Hello and welcome to my YouTube channel Petro Intelligence. My name is Shahid Khan, and I am a chemical engineer. Today we will discuss condensers and tower pressure control and concept of hot vapor bypass. The total condensation of a vapor to a liquid is best illustrated by the condensation of steam to water. This picture is a rather accurate reproduction of the radiator that heated my apartment. Steam flowed from the boiler in the basement. The steam condensed inside the radiator and flowed back into the boiler through the condensate drain line. This is a form of thermosiphon circulation. The driving force for the circulation is the differential density between the water in the condensate drain line and the steam supply line to the radiator, and we have discussed this in video lecture on thermosiphon reboilers. The bigger the radiator, the more heat is provided to a room. The bigger the radiator, the faster the steam condenses to water inside the radiator. A larger radiator has more heat transfer surface area exposed to the condensing steam. Unfortunately, the radiator shown in picture is suffering from a common malfunction. Water hardness deposits have partly plugged the condensate drain line. Calcium carbonate is a typical water hardness deposit. Anyone who has lived in an apartment house in colder areas will have had to occasionally bang on the radiator to increase heat flow. Banging on the radiator often breaks loose the carbonate deposits in the condensate drain line. The steam condensate, which has backed up in the radiator, now empties. This exposes more of the interior surface area of the radiator to the condensing steam. It rather seems that 40% of the surface area of the radiator in picture is submerged underwater. If the water is drained out, does this mean that the rate of steam condensation will increase by the same 40%? Answer is yes. Does this mean that the radiator heat transfer duty will increase by 40%? Answer is not quite. Subcooling and effect of subcooling. When steam condenses at atmospheric pressure, it gives off 1000 BTU/pound of condensing steam. This is called the latent heat of condensation of steam. When water cools off from 220 to 120 degrees Fahrenheit, it gives off 100 BTU per pound of water. This heat represents the sensible heat content of water between 220 and 120 degrees Fahrenheit. It takes less of the radiator's surface area to condense 1 pound of steam at 220 degrees Fahrenheit than to cool off 1 pound of water from 220 to 120 degrees Fahrenheit. And this is true even though the condensation of steam generates 10 times as much heat as the cooling of hot water. Does this mean that it is a lot easier to condense steam than to cool water? Yes. This also explains, then, why condensate backup reduces the rate of heat transfer and condensation. Mechanics of subcooling. As the condensed steam flow out of the radiator is restricted, the surface area of the radiator available to cool the hot water increases. Hence, the water temperature leaving the radiator decreases. To summarize, the effect of restricting the condensate flow from a radiator or condenser is to build the water level in the radiator. Reduce the rate of latent heat transfer from the steam. Increase the rate of sensible heat transfer from the condensate. Reduce the overall heat transfer duty from the radiator. Incidentally, the correct way to remove hardness deposit is by chemical cleaning. Violent banging on radiators is considered bad form in colder areas. What is air lock? Vapor binding, or air lock, is another common cause of household radiator malfunction. Often, the vapor accumulating in the radiator is CO2, rather than air. The CO2 originates from the thermal decomposition of carbonates in the boiler. Regardless, air and CO2 form a non-condensable vapor in the radiator. These non-condensables mix with the steam in the radiator. The non-condensables then reduce the concentration of the steam by dilution. The diluted steam has a lower partial pressure than pure steam. The lower the partial pressure of the steam, the more difficult it is to condense. As the rate of condensation of the steam drops, so does the heat radiate by the radiator. In refinery steam condensation services, in both reboilers and steam turbines exhausting to vacuum surface condensers, I have observed that small amounts of non-condensibles greatly reduce the apparent heat transfer coefficient. In reboilers, propane or butane may leak into the lower pressure steam side of the reboiler. In surface condensers, air could be drawn into the condenser's shell, which operates under vacuum conditions. In the latter case, I've observed that the heat transfer coefficient, which should be 200 BTU per feet square per degree F, is only about BTU per feet square per degree F. It seems these non-condensibles are increasing the heat transfer film resistance by interfering with the ability of the steam molecules to come into contact with the cooler heat transfer surface area. A tiny amount of air in a steam condenser will reduce the rate of the steam condensation by an order of magnitude. To restore the efficiency of a radiator suffering from the accumulation of non-condensibles inside its condensing coils, the non-condensable gases have to be removed. The air vent shown in picture serves this purpose. Vapor binding. We can measure the non-condensable concentration in the flow of a mostly condensable vapor such as steam. However, the actual concentration of non-condensibles in contact with the condensate layer around the tube wall or inside the tube is much greater. While the condensable vapor condenses and drains away as a liquid phase, the only way the non-condensibles can escape from the tube surface is by diffusion backwards against the bulk of the vapor flow. In order to make this diffusion possible, there must be a concentration gradient with a higher non-condensable concentration near the tube surface, which then impedes the condensation rate of the bulk of the vapor flow. You can see this in our ES Silver, Process Instrumentation Mechanical Engineers, Volume 178, pages 351, 1963 to 1964 edition. This explains why a small amount of venting non-condensibles often the dramatic effect of increasing condensation rates has, especially when condensing pure components such as steam. I also believe that this explains a problem that I've seen several times in steam turbine exhaust vacuum surface condensers. That is, an apparent large loss in the steam heat transfer coefficient, due to a relatively small air leak into the vacuum surface condenser's shell. To summarize, the two most common malfunctions of a steam condenser, or radiator, are condensate backup, non-condensable accumulation. And these two malfunctions are also the most common problems we encounter in the design and operation of shell and tube heat exchangers used in total condensation service for hydrocarbons, as well as for steam. Condensation in shell and tube heat exchangers. If what you have just listened seems to be a repetition of the discussion of steam reboilers in my previous video, your analysis is correct. A steam reboiler has the same problems and works on the same principles as a process condenser. The only difference is that a steam reboiler's heat is removed by the shell-side process fluid, and a process condenser's heat is removed by cooling water or air. This picture is a sketch of a depropanizer overhead condenser. Let's make a few assumptions about this shell and tube condenser. The propane is totally condensed as it enters the reflux drum. There is no vapor vented from the reflux drum, but there is a vapor-liquid interface in the drum. The reflux drum is elevated by 20 feet above the top of the condenser. We are dealing with pure, 100% propane. If the liquid level in the reflux drum is located 20 feet above the condenser, does this mean that the liquid level in the pipe feeding the condenser is also 20 feet above the condenser? Is this possible? No. If the pipe to the condenser maintained a liquid level, then the shell side of the condenser would be full of propane. But if the shell side of the condenser were really liquid full, the tubes would not contact the vapor. If the tubes do not contact the vapor, then the rate of condensation is zero. Perhaps a small amount of heat transfer would take place as the liquid propane became subcooled. But none of the propane vapor would condense. Therefore, the liquid level in the overhead condenser would have to be somewhere in the condenser's shell. But then the liquid in the condenser would be below the reflux drum. How, then, does the liquid get from the lower elevation of the condenser to the higher elevation in the reflux drum? We will have to explain this hydraulic problem later. But for now, we can say that most reflux drums are elevated 20 or 30 feet above grade to provide net positive suction head, NPSH, for the reflux pump. Also, most shell end tube condensers are located at grade for easier maintenance during unit turnarounds. Subcooling in a shell end tube condenser. This picture is the same propane condenser shown in previous picture. Let's assume that the pressure drop through the shell side is 0. Again, we are dealing with a pure component, propane. The inlet vapor is at its dew point. That means it is saturated vapor. Under these circumstances, the outlet liquid should be a saturated liquid, or liquid at its bubble point. As the inlet dew point temperature is 120 degrees Fahrenheit, the outlet bubble point temperature should be 120 degrees Fahrenheit. But, as can be seen in picture, the outlet shell side liquid temperature is 90 degrees Fahrenheit, not 120 degrees Fahrenheit. Why? The reason is condensate backup. The condensate backup causes subcooling, that is, the liquid is cooled below its bubble point or saturated liquid temperature. Perhaps a rat has lodged in the condensate outlet pipe. The rat restricts condensate drainage from the shell side. To force its way past the dead rat, the propane backs up in the condenser. The cold tubes in the bottom of the shell are submerged in liquid propane. The liquid propane is cooled below its bubble point temperature. Note that the propane vapor is still condensing to propane liquid at 120 degrees Fahrenheit. The condensed liquid is in intimate contact with the propane vapor as it drips off the outside surface of the colder condenser tubes. The saturated propane vapor condenses directly to saturated propane liquid at 120 degrees Fahrenheit. The saturated, or bubble point, liquid then drips from the condensation zone of the condenser into the subcooling zone of the condenser. This is the zone where the tubes are submerged in liquid. Try running your hand along the outside of such a condenser. Feel for the point on the surface of the shell where there is a noticeable drop in temperature. The upper part of the shell will be hot. The lower part of the shell will be cold. The transition point corresponds to the liquid level of condensate in the shell. The condensate level will always be higher toward the shell outlet nozzle. Again, this all applies only to condensers in total condensing service. Effective condensate backup. When the condensate level in an exchanger increases, the area of the condenser devoted to subcooling the condensate increases. But the area of the exchanger available for condensing decreases. That is bad. When the area of the exchanger available for condensing is reduced, the ease of condensation is also decreased. Depending on the circumstances, one of two unfavorable things will now happen. 1. If the supply pressure of the condensing vapor is fixed, the rate of condensation of the vapor will fall. In an apartment house in Brooklyn, this means that your bedroom will get cold. 2. If the condensing vapor flow rate is fixed, the condensation pressure will increase. If you are operating a debutanizer in Texas City, this means that the tower's safety release valve will pop open and release a cloud of butane over Lamar University. Heat removed by condensation is easy. The heat transfer coefficient U for condensation of pure, clean vapors may be 400 to 1000 BTU per hour per feet square of heat exchanger surface area, per degree F of temperature driving force. The U value for subcooling stagnant liquid may be only 10 to 30. Condensate backup is the major cause of lost heat transfer for heat exchangers in condensing service. Reflux drum elevation increase promotes subcooling. Once upon a time many years ago, a tragic event occurred in Louisiana. A rat entered the condenser outlet pipe shown in picture. The condenser had been offline for cleaning. The rat, having crawled up the riser pipe to the reflux drum, got its head stuck in the drum's inlet nozzle. The engineer, unaware of the rodent's predicament, put the exchanger back into service. The condensed butane now flowed across the rat. The rat died. Well, we all must come to that end eventually, although perhaps not quite that exact end. Such is the way of all flesh. This rat is called a 20-pound rat. Not that the rat weighed 20 pounds. The 20-pound refers to the pressure drop of 20 psi that the liquid encountered as it flowed across the rat's now lifeless body. Before the introduction of this pressure restriction, the butane entering the reflux drum was at its bubble point. Our question is, will the introduction of the rat at the inlet nozzle cause the butane, as it enters the vessel, to flash? The term to flash is used to denote partial vaporization of the butane. Before the rat became stuck, the liquid entering the reflux drum did not flash or partly vaporize. We can also be sure that at steady state the butane liquid did not flash after the introduction of the rat because no vapor was vented from the reflux drum. But let's assume that in the first microsecond after the introduction of the rat the liquid did vaporize. The vapors so generated would be trapped in the reflux drum. The pressure in the drum would increase. Not by 20 psig, but just a little. The small increase in pressure in the reflux drum would push up the liquid level in the condenser. The surface area of the condenser available to subcool the liquid would increase. The liquid temperature would be reduced. As the subcooled liquid flowed across the dead rat, its pressure would drop. The liquid's pressure would fall to exactly that pressure that corresponds to the vapor pressure of the butane at the temperature in the reflux drum. The backup of butane liquid in the condenser would continue until the butane leaving the condenser was cold enough so that it would not flash as it flowed across the rat, that is, until equilibrium conditions had been re-established in the reflux drum. As the butane liquid level in the condenser increased, the area of the exchanger exposed to the condensing vapors would decrease. Let's assume that the tower's reboiler duty was constant. The vapor flow rate to the condenser would then be constant. To condense the same flow rate of vapor with a shrinking exchanger surface area, the pressure of condensation must increase. The tower pressure would also go up as the condenser pressure rose. Forget about the rat. I made that story up. The real story is that the riser pipe connecting the condenser outlet to the reflux drum was undersized. The project engineer specified a 4-inch pipe when an 8-inch pipe was needed. The pressure drop through the pipe was then 32 times higher than the intended delta P of 0.60 psig. Delta P in a pipe varies to the 5th power of the pipe's diameter. The resulting riser pipe pressure drop was 20 psi. This frictional loss of 20 psi in the pipe had the exact same effect on the condenser, and on the tower's pressure, as the 20-pound rat. Forget about project engineer, forget about the rat, both stories are pure fiction. The truth is that the elevation of the reflux drum was 80 feet above the condenser. The specific gravity of the butane liquid was 0.59. This means that 80 feet of liquid exerted a head pressure of about 20 psig. 80 feet divided by 2.31 feet of H2O divided by psi times 0.59 specific gravity butane divided by 1.00 specific gravity H2O equals 20 psig. This elevation head loss of 20 psig had the same effect on the condenser and on the tower's pressure as did the rat or project engineer's frictional loss. Common design error. Please refer back to picture. How can the liquid from the condenser rise to the higher elevation in the reflux drum without being pumped? Simple. The pressure head of the liquid leaving the condenser is converted to elevation as the liquid flows up into the reflux drum. This works fine as long as the liquid leaving the condenser is sufficiently subcooled. By sufficiently subcooled, I mean that when the lower pressure liquid flows into the reflux drum, it has to be cold enough so that it does not flash. The liquid leaving the condenser is subcooled. The liquid entering the reflux drum is saturated liquid at its bubble point. Of course, the temperature of the liquid is the same at both points. The subcooled liquid is subcooled in the sense that its pressure is above the bubble point pressure at the condenser outlet temperature. It is this extra pressure, above the bubble point pressure, that may be converted to elevation. I have another way to explain how the condensed liquid can flow uphill from the condenser into the elevated reflux drum. That is, the liquid leaving the condenser is pushed into the reflux drum by the higher pressure in the tower. This will work okay, as long as the liquid entering the reflux drum is at its saturated bubble point temperature and pressure. If this is not the case, then the vapors flashing out in the reflux drum will have to be vented. If you refuse to open this vent, then condensate backup must increase in the condenser, with a consequent reduction in the condenser's capacity. Tower pressure control. For total condensers, there are three general schemes for controlling distillation tower pressure. Throttling the cooling water flow to the condenser. Flooding the condenser. Hot vapor bypass around the condenser. Regardless of the method selected, the principal concept of tower pressure control is the same. We control the pressure in the reflux drum by manipulating the temperature in the reflux drum. The tower pressure then floats on the reflux drum pressure. To lower the tower pressure, we must first cool the reflux drum. This reduces the vapor pressure of the liquid in the reflux drum. The oldest, most direct method of pressure control is throttling on the cooling water supply. This scheme is shown in picture. Closing the water valve to the tube side of the condenser increases the condenser outlet temperature. This makes the reflux drum hotter. The hotter liquid in the reflux drum creates a higher vapor pressure. The higher pressure in the reflux drum increases the pressure in the tower. The tower pressure is the pressure in the reflux drum plus the pressure drop through the condenser. Throttling on the cooling water works fine, as far as pressure control is concerned. But if the water flow is restricted too much, the cooling water outlet temperature may exceed 125 to 135 degrees Fahrenheit. In this temperature range, water hardness deposits plate out inside the tubes. Then the heat transfer coefficient is permanently reduced by the fouling deposits. Hot vapor bypass and hot vapor bypass pressure control. A more modern way of controlling a tower's pressure is shown in picture. This is the hot vapor bypass method. When the control valve on the vapor bypass line opens, hot vapors flow directly into the reflux drum. These vapors are now bypassing the condenser. The hot vapors must condense in the reflux drum. This is because there are no vapors vented from the reflux drum. So, at equilibrium, the hot vapors must condense to a liquid on entering the reflux drum. They have no other place to go. The latent heat of condensation of this vapor is absorbed by the liquid entering the reflux drum. The liquid that enters the reflux drum comes from the condenser. The hot vapor mixes with the condenser outlet liquid and is condensed by this cooler liquid. Does this mean, then, that the condenser outlet temperature is lower than the reflux drum outlet temperature? If I were to place my hand on the reflux pump suction line, would it be warmer than the condenser outlet? Answer is yes. But the liquid in the reflux drum is in equilibrium with a vapor space. This liquid is at its bubble, or boiling point. If the liquid draining from the condenser is colder than this bubble point liquid, it must be subcooled. But how can a vapor condense directly into a subcooled liquid? Well, it cannot. The tower overhead vapor, shown in picture, condenses to a liquid on the outside of the cold condenser tubes. The liquid drips off the tubes. These droplets of liquid are in close contact with the saturated vapor in the condenser shell. This means that the liquid is in equilibrium with the vapor. The condensed liquid is therefore initially at its bubble point temperature. This liquid accumulates in the bottom of the condenser's shell. The submerged tubes then must subcool this liquid. Part of the surface area of the condenser is hence devoted to subcooling liquid, and part is devoted to condensing vapor. But how does this work? How does the condenser know, without any advice from us, how much of its heat exchanger surface area, which is supposed to be used to condense vapors, to divert to subcooling liquid? Let's assume that the liquid draining from the condenser is not quite cold enough to absorb the entire latent heat of condensation of the vapors flowing through the hot vapor bypass line. The vapors will then be only partially condensed. Vapor will start to accumulate in the reflux drum. This accumulation of vapor will increase the reflux drum pressure by a small amount. The higher drum pressure will back up the liquid level in the condenser by a few inches. The higher height of liquid in the drum will submerge additional cold tubes with the condensed liquid. The cooler liquid will now be able to absorb more of the latent heat of condensation of the vapor passing through the hot vapor bypass line. Eventually, a new equilibrium will be established. What if the hot vapor bypass valve is leaking? Let's assume that the hot vapor bypass valve, shown in picture, is leaking. It is leaking 10% of the tower overhead flow. A good rule of thumb is then, for hydrocarbons, for each 20 degrees Fahrenheit temperature difference between the cooler condenser outlet and the warmer reflux pump suction, 10% of the tower's overhead vapor flow is leaking through the hot vapor bypass valve. For aqueous systems, for each 20 degrees Fahrenheit temperature difference between the condenser outlet and the reflux pump suction, 1% of the tower's vapor flow is leaking through the vapor bypass valve. As the hot vapor bypass valve opens, the condensate level in the shell side of the condenser increases to produce cooler, subcooled liquid. This reduces the surface area of the condenser exposed to the saturated vapor. To condense this vapor with a smaller heat transfer area, the pressure of condensation must increase. This, in turn, raises the tower pressure. This, then, is how opening the hot vapor bypass pressure control valve increases the tower pressure. Incidentally, as I have shown in pictures, the condenser may be located above or below the reflux drum. Both configurations require a subcooled liquid effluent from the condenser. But if the condenser is located below the reflux drum, additional subcooling to offset the elevation effect, described above, will be needed. Flooded condenser pressure control. You should have concluded by now that hot vapor bypass pressure control actually works by varying the surface area of the condenser exposed to the saturated vapor. But why do this indirectly? Why don't we simply and directly vary the liquid level in the condenser, shown in picture? The answer has something to do with women's clothes. Perfectly good, sensible designs go out of fashion. The perfectly good, sensible design used to control a tower's pressure, flooded condenser control, shown in picture, has gone out of fashion. In a flooded condenser tower pressure control strategy, the reflux drum is run full. Restricting the flow from the reflux pump increases the level in the condenser. This reduces the heat transfer surface area available for condensation and raises the tower pressure. Either the reflux or overhead product flows may be used to vary the liquid level in the condenser. Once a liquid level reappears in the reflux drum, the condenser capacity has been exceeded. The level in the condenser will continue falling until the drum empties and the reflux pump begins to cavitate. In general, flooded condenser pressure control is the preferred method to control a tower's pressure. This is so because it is simpler and cheaper than hot vapor bypass pressure control. Also, the potential problem of a leaking hot vapor bypass control valve cannot occur. Many thousands of hot vapor bypass designs have eventually been converted at no cost to flooded condenser pressure control. The function of the reflux drum in a flooded condenser design is to separate water from reflux when distilling hydrocarbons. Give the operators time to respond if they have exceeded the condenser's capacity. Provide a place from which non-condensable vapors may be vented. One problem with flooded condenser pressure control is related to the need to occasionally vent non-condensibles. This vent valve must not leak when closed. Since the drum is normally full of liquid, a leaking vent valve will pass liquid. Many pounds of product can be lost in this way. A butterfly control valve with a soft, rubberized seat is a good choice for a remotely controlled, non-condensable vent valve. Air-cooled condensers seem to work as well as shell and tube water coolers in flooded condenser pressure control service. Some air coolers are sloped toward the outlet to reduce the ratio of the delta condenser surface area to delta height change of condensate backup. I don't think this is necessary, but it may help in fine-tuning pressure control with air-cooled flooded condensers. But don't just take my word for it. Try running on flooded condenser pressure control rather than hot vapor bypass, and I think you will be quite pleased with the result. Partial condensation. If we normally have a situation in which non-condensable vapors appear in the reflux drum, then there is only one pressure control option available. This is to place the tower pressure control valve on the vapor off gas as shown in picture. If we normally have non-condensable vapors in the condenser effluent, then the following problems we have been discussing do not exist. Condensate backup. Subcooling of condenser effluent. Fouling due to low flow of the cooling water tubes. Sometimes we see tower pressure control based on feeding a small amount of inert or natural gas into the reflux drum. This is bad. The natural gas dissolves in the overhead liquid product and typically flashes out of the product storage tanks. The correct way to control tower pressure in the absence of non-condensable vapors is to employ flooded condenser pressure control. If, for some external reason, a variable level in the reflux drum is required, then the correct design for tower pressure control is a hot vapor bypass. Slug flow in risers. Picture illustrates a common cause of an erratic tower operating pressure. The condenser effluent is a two-phase mixture of vapor and liquid. In the summer, the tower pressure is steady. But in the winter when the cooling water is cold, pressure control is erratic. The problem is phase separation in the riser line. The vertical velocity in this line is too low to maintain a froth flow up the riser. Slugs of liquid form. Periodically, the accumulating liquid is blown out by the vapor. This slug flow causes an erratic back pressure on the tower but not an erratic pressure in the drum. This problem only occurs when the drum is elevated above the partial condenser. The fundamental difficulty is excessive riser pipe diameter. To avoid slug flow in such a riser, a mixed phase velocity of at least 20 feet per second is needed. While the 20 feet per second may be maintained in the summer, more efficient condensation in the winter may reduce vapor flow. This can cause the riser velocity to drop below the minimum to prevent phase separation. Throttling the cooling water will stabilize the tower pressure but may result in salting up the exchanger with water hardness deposits. That's all, gentlemen. If you like my video, please follow my YouTube channel Petro Intelligence for more videos. Good day and good luck.